Good morning. Good morning to all. So let us start our session MCS230 2D transformation. So the last class we had a discussion of 2D transformation. Why 2D transformation? The proper definition is here. You see the 2D transformation in computer graphics are mathematical operations used to modify, reposition. You can change the position and you can change the size, alter the size, or make any orientation, rotation of shapes and image within a flat two-dimensional plane. In a flat two-dimensional plane, so that is why the name is 2D transformation. These operations recalculate the coordinate point of an object using some algebraic equation and matrix systems. We use some matrix algebra here to represent the different type of transformations. uh, Transformation play an important role in computer graphics to reposition the graphics on the screen and change their size and orientation. We have the various type of transformation. Please recall these are the important transformation: translation, scaling, rotation, reflection, and shearing. And we know that translation is used to change the location. Scaling is used to change the size of the object. Rotation, you can rotate the object either any direction, clockwise or anti-clockwise. Then reflection also there. That is, you can find the mirror image of an image with respect to the origin or on any other line. Shearing, to change the shape of the object. So a rectangle may change to a square may change to a rhombus, or it is so when a transformation takes place on a 2D plane, it is called 2D transformation. So as it is takes place in a 2D plane, the two-dimensional plane, that is why the name is 2D transformation. And you know these are the objectives. Yeah, in this session, we will discuss what are the different objective of the 2D transformation: translation, rotation, scaling. Other two are also there: reflection and shearing, and homogeneous representation and coordinates. So when we apply composite transformation to an object, to a body, uh, the composite transformation means we can apply one transformation followed by other. Suppose you want to uh, change the direction or rotate the object as well as change the size. So you can first apply your rotation followed by scaling. This is known as composite transformation. That is, if you apply more than one transformation to one body, this is called composite transformation. So for transformation, composite transformation, we need a homogeneous representation of coordinate. Let us see what is homogeneous. You see, homogeneous coordinates. To perform a sequence of transformation such as translation followed by rotation and scaling, we need following process. So to perform composite transformation, one transformation followed by others, here such as translation followed by rotation and then scaling. So we need following sequence of process. What is translate the coordinate, rotate the translated coordinate. So once the translation is done, then rotate that and then scale the rotated coordinates to complete the composite transformation. So to a single object, we first perform translation, then rotation, and then scaling. To shorten this process, we have to use a 3 cross 3 transformation matrix instead of a 2 cross 2 matrix. So as you know, as it is two-dimensional transformation, so the representation is a 2D matrix. But to make the process simpler, to perform the composite transformation easily, we use 3 cross 3 transformation matrix instead of 2 cross 2 matrix. To convert it to 2 cross 2 matrix, 3 cross 3 matrix, we have to add an extra dummy coordinates. That coordinate not exist, so we have to add that dummy coordinate. In this way, we have an example. I mean, we will discuss when we will learn composite transformation. So in this way, we can represent the point by 3 numbers instead of 2 numbers, which is called homogeneous coordinate. So to use a 3 cross 3 transformation matrix instead of a 2 cross 2 matrix transformation matrix, we have to add an extra dummy coordinates, extra row and extra column. So a 2 cross 2 matrix now become a 3 cross 3 matrix. So we can represent the point by 3 numbers instead of 2 numbers. So which is called homogeneous coordinate. Basically, a number is dependent by 2 numbers, x axis and y axis. But we can represent that number in 3 numbers. We'll discuss. We have an example in next slides. So when we discuss composite transformation, we'll discuss about that. So, but you remember that this is known as this. You only know that is now, which is this is the homogeneous coordinate. Besides these two, other two transformations there, reflection and shearing. Reflection used to find the mirror image, and shearing used to change the shape of the object. We have already discussed geometric transformation. Changing the object position is known as translation. Rotating the object or orientating the object is called the rotation or orientation. Or changing the size is known as scaling. And other two transformation is reflection and shearing. Shearing used to change the shape with respect to any line or origin. And reflection also to give a mirror image of an image with respect to axis or any pivot line. This is your 2D transformation. You see, this is a 2 cross 2. This is a matrix from P dash equal to P plus T. Initially, it was in P. And after applying the translation, now it is changed to P dash. So now I am able to change the position of a point to another point, P to P dash, using the translation factor Tx and Ty. So x dash is calculated by x plus Tx, y dash equal to y plus Ty. So initially it was in x, y, P, and after applying translation now it is moved to the P dash. So now we are able to move a point P to P dash. Similarly, if there is a line, to move a line segment, apply the transformation equation to each of the two line endpoints. You need not to apply the translation equation to all the point of the line. Only you need to translate two endpoints of a line. Previous example, there is a single point. So we don't have any problem. But in case of a line, you know that a line consists of several points. You need not to apply translation equation to all the points of the line. You only need to apply the translation equation only to endpoints. So now the two endpoints gets its another position and then redraw it. redraw it, and you will get a new line. So that is similarly, to move a polygon, apply the transformation equation to coordinate of each vertex and regenerate the polygon using the new set of the vertex. Suppose there is a rectangle, you need to apply the transformation equation to four vertices, not all the points, only four vertices. So after applying that four vertices moves, you will get a new set of vertices. Redraw or join these four vertices, and uh, you will you are able to now move the polygon. You see the rotation, 2D rotation. Suppose there is a object, we have to rotate either clockwise or anti-clockwise with respect to a specific angle theta, 60 degree, 45 degree, 90 degree, 180 degree. You can rotate an object. So this is the axis. So rotation axis, we need to perform the rotation. We need three things. One is rotation axis, another is rotation angle theta, and that is the rotation point with respect to which point we have to rotate. Either it is origin or any other point known as the pivot point. So these are not the rotation point. So the direction of the rotation depend upon the theta, the rotation angle. So direction of a rotation depend upon the rotation angle theta. If theta is positive, the rotation is anti-clockwise, counterclockwise. If theta is negative, so it is clockwise. So rotation, the angle of rotation depend upon the angle theta. So remember that you know that if you apply cos theta, cos A plus B, it is cos A dot cos B. Will sin A into sin B. This is the formula of cos A plus B and cos A minus B. If cos A plus B, there is a negative sign, and cos A minus B, cos A into sin B plus sin A into cos B. Let us see. 2D rotation. Suppose there is a point x, y. You see, there is a point x, y. Suppose this point is P, and uh, we have to rotate that point towards anti-clockwise to P dash, x dash, y dash. Initially it was x, you see there's a point x, y, and at first suppose the pivot point at the origin. So the with respect to origin we have to rotate. So you see I joined the origin. The line is joined to the origin to xy. That means this is the rotation point is the origin. We can rotate that point with other than any point other than the origin. That is not the pivot point. So here pivot point is the origin. So suppose the pivot point is origin. So s dash equal to r cos theta plus phi. So phi is the initial angle and theta is the rotation angle. So total angle will be formed of theta plus phi. Initially is a phi, then theta is a positive direction. So the final angle will be theta plus phi. So we know that x bar equal to r cos theta plus phi. So r is the distance from the origin to x and y. Here r is nothing but it is the distance from the point xy from the origin. So r cos theta into cos phi minus r sin theta cos phi. Sin phi. This is the formula of cos a plus b. In previous exam written. Similarly, y dash equal to r cos theta sin theta plus r sin theta plus cos phi. So x is equal to r cos phi, y is equal to r sin phi. So x dash is equal to s cos theta minus y sin theta, and y dash equal to r sin theta plus cos theta. And this is the transformation matrix. But you see, this is not the homogeneous coordinate. So R is a 2D geometric, so we can use this formula. This is the 2D rotation का formula, P dash equal to R dot P. So what is R? Cos theta minus sin theta, sin phi, cos phi. So this is R. And you will get P dash by multiplying R into P. P is the initial point. And the new point or new after rotation, the final point is equal to R dot P. If you multiply two matrix R and P. So rotation of a point about any specified position, not origin. Okay, so these are the xr and yr. So x dash equal to xr plus x minus xr cos theta minus y minus yr sin theta. So this is the rotation about a point other than the origin, xr, yr. So we have already discussed. You can rotate an object with respect to origin or any other point. The previous example was about the origin. You see, this is the origin. But now, if you want to rotate a point about any specified position other than the origin, 0, 0, so it is xr, yr suppose. So also, this formula is used. S dash is equal to sr plus x minus sr cos theta minus y minus yr sin theta. And y dash is calculated exactly the same formula. So rotation also move object without deformation. So there is no deformation, there is no change in other information of the object. A line is rotated by applying the rotation formula to each of the endpoint and redrawing the line between the new endpoints. So this is the formula of rotation of a point only. But we can rotate a line. You know that the line is consists of several points, and every line has two endpoints. So apply the rotation formula to only to the endpoints only, like your translation. So applying rotation to two endpoints, you will get the another location with these 2 points. You redraw that, join that 2 points. So a line is rotated by applying the rotation formula to each of the endpoints and then redrawing the line between the two endpoints. Similarly, polygon, a triangle, a rectangle, a hexagon, so can be also redrawn only applying the rotation formula to each of the vertices. We need not to apply the rotation formula to each and every points of the line. So as a polygon have some vertices, rectangle has 4 vertices, triangle has 3 vertices. So you only apply the rotation formula to those endpoints only. So and then redrawing the polygon using new vertex coordinate. So after applying the rotation formula, you will get a set of new vertices. So you join them, redraw the polygons using the new vertex coordinate which is newly formed, and so that in this way we can rotate a polygon. So this is a algorithm, 2D rotation routine. This is not required for you. Third one, scaling. You see, uh, we have so far we have discussed two major 2D transformation. One is translation, another is rotation. So, third one is scaling. As we all know, scaling is used to alter the size of an object. You can change the size. So we can enhance the size or degrade the size or decrease the size. Simple 2D scaling is performed by multiplying object position xy by scaling factor xs and xy. So there are some translation factor tx and ty which is added. Please recall the translation. Translation is used to translation factor is added to x and y, but here the scaling factor is multiplied. You see x dash equal to x into sx. The x dash, the new x value can be calculated the original x value multiplied by the scaling factor. Sx means the scaling factor about x axis. But please recall, in place of translation, what we used to do, that is we at that time we are multiplying. Sorry, we are adding. That is x dash is equal to x plus tx. Here x dot sx. Similarly, y dash is equal to y into sx. And if we represent in a matrix form, you see s dash y is equal to sx 0 0 sy into xy. So if you multiply the matrix, you will get the same result. S dash equal to sx into x plus 0 into y. That is 0. So x dash equal to s dot sx. Similarly, if we multiply the second row uh, with the first column, so it will 0 into x, 0 into x plus y into sy or sy into y. So this is the matrix representation. So we have the matrix representation of a 2D translation. But remember, it is not a homogeneous coordinate. We will discuss about the homogeneous coordinate. Homogeneous coordinate 3 row and 3 column. The same thing is there, but we have add an extra row and extra column, dummy row. Okay, so but so far we are using only 2D. But when we are applying the composite transformation, we must take the help of homogeneous coordinate. So this is a matrix of order 2. So shortly you can write P dash equal to S dot P. What about the scaling factor? The size of the object, either you are to increase the size or decrease size, depend upon the scaling factor. So any positive value can be used as scaling factor. Values less than 1. If the value is less than 1, suppose 1.2, 0.5, 0.75, but scaling factor is always positive. It is either greater than 1 or less than 1, but it is always positive. It is greater than 0, always. So any positive value can be used as scaling factor. Values less than 1 reduce the size of the object. So from the scaling factor, we will able to know that whether we are going to increase the size or decrease the size. If the scaling factor value is less than 1, then the object is to be reduced. If the value is greater than 1, the object to be enlarged or increase in size. If the scaling factor is exactly 1, the object stays unchanged. If you multiply 1 with any number, you know that that is the size remains same, the values remain same. But if you multiply a number which is greater than 1, the size will be increases. If you multiply a number with 2 or 3 or 5, the size will be, the value will be increases. Okay, if a positive number, in case of a positive number. Similarly, if we multiply a number which is less than 1, so the value decreases. So 50 into 1 by 2. 1 by 2 is less than 1. So the value is 25, which decreases. So if the scaling factor is less than 1, the value decreases. If it is greater than 1, the size increases. If it is exactly equal to 1, the size remains unchanged. There will be no change in size. So if Sx equal to Sy, if they are equal, this is called the uniform scaling. That is, we are enlarging the size or distributing size in a uniform manner, in the same ratio in the x-axis and y-axis. So this type of scaling is known as uniform scaling. Suppose x is equal to 5, Sy is equal to 5. Suppose x is equal to 1 by 2 or Sy is 1 by 2. If they both are same, so this type of scaling is known as uniform scaling. If the factor is greater than 1, then the object moves closer to the origin. If the factor is less than 1, so the object moves to the closer to the origin. You see, this is x and x dash. So here our initial was x. Now you see x dash is smaller. So what do you think? What is the scaling factor? The scaling factor here must be less than 1 because the size decreases. So if size decreases, you see the line is closer to the origin. The line comes to the closer because SS and x-axis y-axis value decreases. So decreases means it comes closer to the origin. Similarly, if the scaling factor greater than 1, then the object moves further than origin because the value of x-axis and y-axis increases. If it increases, this the distance from the origin will be larger. So from this, we will know that is the scaling factor plays a vital role here. So depending upon the values of scaling factor, we are able to know that how the reduce of the size. So if the scaling factor is less than 1, the object moves closer and to the origin. If the scaling factor greater than 1, then the object moves further than the origin. So from the picture we know that the size of the object decreases, but you know that you see that the object is closer now to the origin. Initially it was x, now the x dash, the size decreases and it becomes the closer to the origin. We can control the location of the scale object by choosing the position called the fixed point. So we can also make the scaling with respect to any other point, any other point beside the origin. We'll also discuss about the lateral sided. There is a good example with some graphics are there. But you remember only that we can also apply the scaling factor with respect to any other point other than origin, and it is known as the fixed point xr, xf and yf. So here the calculator has show x minus xf equal to x minus sf into sx, and y dash equal to minus yf equal to y minus yf into sy. So this is the formula of a scaling with respect to any other fixed point other than the origin. But in previous case it was origin. You see, this is origin. With respect to origin we are applying the scaling factor, but you can also make the scaling factor with respect to any other fixed point other than the origin. Matrix representation and homogeneous coordinate. We have already discussed about the homogeneous coordinate. It is basically need for a composite transformation. Suppose we have already discussed three different transformation: translation, scaling, and last one is rotation. But if we apply simultaneously one by one in a single object, suppose translation followed by your scaling followed by rotation. So in this case, to calculate easier or perfectly, we need a homogeneous coordinate. Many graphics application involves sequence of geometric transformation. Sequence of geometric transformation one by one. And uh, for example, animations. If you want to animation of an image, design and picture construction applications, we will now consider matrix representation of these operations. Sequence of transformation can be effectively processed using matrices. That is P dash equal to M1 plus P plus M2. P and P dash are column vectors. M1 is a 2 by 2 array containing multiple factors, multiplicative factors. M2 is a 2-element column matrix containing translational terms. For translation, M1 is the identity matrix. For rotation or scaling, M2 contains the translational term associated with the pivot point or scaling fixed point. So to produce a sequence of operation, composite transformation, such as scaling, followed by rotation, then translation, we could calculate the transformation coordinate one step by step at a time. So if you produce a sequence of transformation, one followed by another, we calculate the transform coordinate one step at a time. A more efficient approach is to combine transformation without calculating immediate coordinate values. So you combine the transformation. So we can first combine the transformation. Then after that applying the without calculating the intermediate coordinate values. So if you calculate the first transformation followed by second followed by third, it takes more time. So we need to an efficient approach, an efficient way. Let us see what is an efficient way. Multiplicative and translation term for a 2D geometric transformation can be combined into a single matrix if we expand the representation to 3 by 3 matrices. So suppose we have to apply translation followed by rotation followed by scaling. We need not to apply the translation one by one. 3 matrix one by one. We only used a combined matrix, a single matrix to the object and get our answer and get our result. So for this, we need to represent this matrix by a 3 cross 3 matrix, by a matrix whose order is 3. We can use the third column for translation terms, and all transformation equation can be expressed as matrix multiplication. You see here, expand a 2D coordinate xy to 3-element representation SH, YH and H called homogeneous coordinate. So now we can use a matrix of order 3 in place of the order 2. So let us see how. H is the homogeneous parameter such as x equal to sh by h or y is equal to yh by h. Infinite homogeneous representation for a point. A convenient choice is to choose h equal to 1. If you take h equal to 1, so that should be the element, the three element representation sx, yh and 1. So x equal to sh and y will become yh because the value of h is 1. You see. Matrix representation and homogeneous coordinate. In previous, we have a 2D matrix. Same translation matrix, but see how it is represented in a matrix of 3 cross 3. S dash y dash 1 equal to translation matrix. You see, this is a 3 cross 3 matrix. 1, 0, tx. If we multiply, S dash will be 1 into x plus 0 into y plus tx into 1. That means S dash equal to tx plus 1 or 1 plus tx or tx plus 1. So S dash equal to s plus tx. We know that the x dash equal to x plus tx. If we multiply the first row and the first column, there's one column only. So 1 into x plus 0 into y for tx into 1. So finally x dash equal to x plus tx. You recall this is the original translation matrix equation. S dash equal to s plus tx. Similarly, if we multiply the right hand side, I am discussing the right hand side. If we multiply the second row with the first column, 0 into x plus 1 into y plus ty into 1. So y dash equal to y plus ty. You see, now I am added another row. Now you multiply the third row with the first column from the right hand side. 0 into x plus 0 into y plus 1 into 1. So 1 equal to 1. So now I am able to represent a 2D translation matrix into a 3D one. One minute. So let us start. This is the matrix representation, and you see how a 2D translation matrix can be written using a 3 cross 3 matrix. I have taken a dummy row. You see, the first row is 1 0 0. The first column, you see, the first column, a dummy column is 1 0 0, and the last column, last row 0 0 1. This is added in a 2 cross. Initially it was 0 tx 1 ty. Initially the matrix was 0 tx and 1 ty, but I have added an extra row and extra column. Extra column means the first column 1 0 0, and extra row is added 0 0 1, the last row. The extra row is the last row and the extra column is the first column. So now we can get a 3 cross 3 matrix. So you see how I can write a 3 cross matrix for a 2D matrix. This is needed for sequence of transformation from composite transformation. Similarly, you see this is a rotation matrix in homogeneous coordinate. We have added an extra row and extra column. The last column is the extra column added, and the last row is the extra row added. So initially it was cos theta minus sin theta, cos theta, a 2 cross 2. But now it became a matrix of order 3, and this is the use of homogeneous coordinate for rotation matrix. If you multiply the two matrix of the right hand side, you will get the same formula or same equation as a 2D rotation 2D matrix. So here P dash equal to R dot P. Similarly, you see 2D scaling matrix. So please recall in case of non-homogeneous coordinate or 2D matrix, we have Sx0 0 Sy. The scaling matrix was Sx0 0 Y. Here also we have added the extra column, the last column, and the extra row, the last row. Okay, so now this is a scaling matrix using homogeneous coordinate. So this is a representation of a scaling matrix using homogeneous coordinate. So far we have discussed the different 3 types of transformation, translation, rotation and scaling, and how to convert a 2D matrix of translation, scaling and rotation into their homogeneous representation, that is the matrix of order 3. Now inverse transformation, or the name suggests inverse, it works exactly opposite to translation. What does the translation do? The translation moves a point from one location to another location. Exactly in opposite way, the inverse transformation moves back to that translated point to the is original point. Okay, suppose a point is moved from P to P dash, applying translation, and if we apply the inverse transformation, that is inverse translation, so the point from P dash again moves back to P. So for translation it is P to P dash, inverse translation P dash to P. So 2D inverse matrix is the T inverse, it is represented by T inverse is 1 0 minus Tx. So please recall, for translation matrix there is a plus Tx. Tx is positive sign, but here Tx is negative sign. So that means we are added there. Now we are subtracting. So 0, 1 minus ty, 0, 0, 1 for homogeneous coordinate system. Here only tx and ty are subtracted, having minus sign value. That is opposite to the sign value of your translation. So by the way, T inverse into T equal to I. So if we multiply this, we will get an identity matrix. Identity matrix, that is, you will get the same original position. I stands for identity matrix here. Similarly, inverse transformation also. You see it was minus cos theta, here is minus sin theta. So if we rotate an object for a specific direction, clockwise or anti-clockwise, with a specific angle theta, applying inverse rotation matrix, we will get our original position. Suppose a point is rotated to another point, that is a theta or 90 degree, or line is rotated to 90 degree. So we have to, suppose we need our original line, we need to apply the inverse rotation matrix. Similarly, 2D inverse rotation matrix, if theta is negative, it is clockwise. So in R inverse, all equal to I. So if we multiply R inverse with R, we will get an identity matrix. We know that is 5 when multiplied with inverse of 5, 1 by 5, it will get 1. 1 is called the multiplicative inverse. So here in case of matrix, the unity matrix is also known as the multiplicative inverse. If we multiply two matrix, one is inverse of each other, so we will get an unity matrix that is dependent by I. Only sign function is affected. Only sign function is repeated. Therefore, we can say R inverse equal to R transpose. Two D inverse scaling matrix. Only you see Sx is multiplied here in previous one, but in inverse scaling matrix, Sx is divided. That is multiplying 1 by Sx. That means Xx is divided. So suppose you change the size of an object by using the scaling transformation, but now you want to reverse back your operation, scaling operation. That is, you want to retain the original size. So now apply inverse scaling matrix. Suppose the size is changed. Suppose there is a line. You apply scaling factor. The line is reduced. Suppose you want to retain your size of that line, the original size. You want to your original size back. So apply inverse scaling matrix using this formula. That is the 1 by Sx 0 0. Similarly, if we multiplied S inverse and S, it will also got inverse matrix. This one is inverse of each other, so it will get unity matrix. So we can set up the sequence of transformation as a composite transformation matrix by calculating the product of the individual transformation. Composite 2D translation. If two successive translations are applied to a point P, then the final transport location P dash is calculated as. You see, we have now applying composite transformation. That is one transformation followed by other. Suppose we want to apply two translation transform to a single point. That is one translation followed by another translation. So suppose you one move to point another point, then move that point to another position. Suppose A to B and B to C. If you want to a point A to B, it needs a translation. And then you want to move that B point to C, it is also need another translation. So it is called the composite translation. A translation followed by another new translation. So here you see we need not to apply two translation one by one. What to do you see? You only simply multiply two translation matrix, get another new matrix, and apply that point finally. So now A is directly transferred to C. You see 1 0 2x 2y 1. So now the final is 1 0 t 1x 2 ty. Suppose we suppose translation for the tx first was 2 then 3. Now it become 2 plus 3 5. Similarly, 2 first y equal to suppose 3, then is 4, so that is 7. So now apply the resultant matrix are the translation matrix. Similarly, you see, in case of composite 2D rotation, so we first multiply the first two, theta 1, one is for theta 1 and the theta 2. That is, we first want to rotate the angle theta, then the angle theta 2. Suppose first we want to do 30 degree and suppose then 60 degree. So we have to apply 90 degree. So here we are adding the theta 1 plus theta 2 and we apply the resonant matrix to the coordinate to get the new one. Similarly, in case of composite 2D scaling, you see the two scale factors multiplied. Suppose the first scale factor is 1 by 2 and second is suppose 3. So 1 by 2 into 3, 3 by 2 is applied. You see. So you need not to apply the first scaling matrix, then second, followed by third, fourth, followed. No. You only multiply the scaling two matrix and the result matrix is multiplied to the original matrix to get the new one. So x s2 sy2 dot x1 sy2 equal to x into xs1 dot into xs2 comma sy1 into sy2. So two scaling factor is multiplied and then applied to the point to get the new point. Successive translation are additive. There are some properties. Successive scaling are multiplicative. You know that in case of successive translation, we add two translation factor. But in case of scaling, we multiplied Sx into xy. For example, if we triple the size of the object twice, then finally size is 9 times the original. Suppose the first point, suppose you want to 3 times first and then again 3 times. So the original size is enhanced by 9 times. That is why so scaling factor is multiplied. General pivot point rotation. Uh, so far we have discussed the rotation with respect to origin. Please recall, in previous slide we have discussed the uh, um, rotation about origin. Yeah, so there is a line from origin to P, which is represented by R. Please recall in previous slides. But now we are going to rotate a point with respect to any other point other than origin, and that point is referred as pivot point. So to perform the general pivot point rotation, we need some steps. The first step is translate the object so that the pivot point is moved to the coordinate origin. You know that the pivot point is not the origin, but first thing is you translate that pivot point to the origin. So that pivot point now is treated as the origin. It moved to the origin. Then rotate the object about the origin. We know how to rotate an object in the origin because the pivot point is now in the origin. We have moved the pivot point to the origin by using translation. We know that the translation is used to move a point from one point to another point. So that is why we translate the object so that the pivot point move to the coordinate origin. So once the pivot point comes to moves to origin, now it is easy to perform the rotation. You know that we have performed rotation with respect to origin. So once the rotation is done, again use the opposite operation that done in step 1. Translate the object so that the pivot point is returned to the original position. So again we are using the inverse translation to take that pivot point from the origin to its original location. So these 3 steps required to for general pivot point rotation. Let us see. There's a good example. You see, this is an object, and we have to rotate it. About that point, you see there's a point. The first one we have to rotate about that origin, about that point, pivot point, not the origin. Suppose in first figure, suppose there is no origin. So this is the object. We have to rotate that object either clockwise or anti-clockwise. So you see there's a pivot point. Now I want to rotate that object with respect to that pivot point. But there is no direct formula for pivot point. We have to move that point to the origin. You see, I am using a translation, and that point is moved to the origin. You see, that point is moved to the origin. Now, the object is at the origin with the pivot point at the origin. So the object is moved with, and the pivot point is now is on origin. It coincides with the origin. Second picture. So we have done the first step. First step is simply translate that point to the origin. I have done that. What is the second point? Now rotate. You see, now rotate 90 degree. Suppose theta is 90 degree. I am rotating anti-clockwise at 90 degree. Now it is rotated. Second step is done. But this is the rotation about the origin. But I need to rotate the object with respect to that pivot point. So again, perform the opposite operation done in first step. Take back to the pivot point from the origin to its original position. You see where the original position in the first case. The first figure, the pivot point is the original position. I have to now convert to that. Move that point, pivot point to its original position using inverse translation transformation. Inverse translation. You see. This is the third step. Now I am able to rotate the object with respect to the pivot point, not the origin. It involves three different steps. First, the translation, that pivot point to the origin. To move that pivot point to the origin, we need translation. So once it comes to the origin, the pivot point coincides with the origin. There is no problem for rotation. Simply rotate the object. And then taken back that pivot point to its original position by using inverse translation. So it is easy method. So in matrix form, the same is represented by you see. The first one, the translation matrix. You see 1 0 XR 0 1 YR 0 0 1. This matrix is a coordinate system, is a homogeneous coordinate. And the second, the rotation matrix, you see cos theta minus sin theta 0 sin theta cos theta 0 0 0 1. This is the rotation matrix. So now rotation done. But to see the third one is the inverse translation. Is the inverse translation. Minus XR and minus YR is there. That is the opposite sign of the translation. The TX and TY or X and Y have the opposite sign of the original. And if we multiply this, you will get the final result. But this one, the three steps. First is translation, then rotation, then inverse translation. So what we done in the previous slides, we are now representing matrix form, matrix operation. That is why you see here need of the homogeneous coordinate system. It may not be possible if the homogeneous coordinate is not applied, because we know that matrix multiplication is not commutative. Not commutative. That is, if A and B are two matrix, AB may not equal to BA. Okay, so AB may not equal to BA. So matrix multiplication is not commutative. So a homogeneous matrix is needed for that. So that is why if you don't take the homogeneous coordinate system, so this may not be possible. Similarly, general fixed point scaling. Same steps, that is, we can scaling with respect to another point, not the origin. In previous one, we saw the origin which scaling operation takes place in with respect to the origin. But now any other point or any other fixed point. Same process is there. Translate the object so that the fixed point coincide with the origin. Then perform the scale the object about the origin. So once it is scaled, translate the object so that the pivot point is returned to the original position. You see here, the same example is there, but here the fixed point is here XR and YR. You see, I want to apply here scaling transformation. That is, I want to change the size. In the previous one, we performed which operation? Rotation operation. Now we are going to apply the scaling. The object should be scaled, but with respect to X and Y. So as per the first step, we need to convert this, translate the point to the origin. You see, we use the translation matrix. So that point is now converted to the move to the origin. So now XR and YR become XY00 or origin. So once it's come the origin, you apply the scaling factor. You see, I applying the scaling factor. You see, it change the size. So now take back that point to the original position XR YR, which was in the first figure, using inverse translation. So this is the matrix form. First is the translation matrix. You see 10x f 01 yf 001. So in place of tx and ty, it is written as xf and yf are the translation factor, and we apply then the scaling matrix is there. Sx00 sy0001. The scaling matrix is applied to the object after it is translated to the origin. So once it is scaled, you see, we are using the inverse translation matrix where xf and yf are change their sign, minus sf and minus sy. 1 0 minus xf 0 1 minus yf 001, and after multiplied you will get the final resultant matrix. But uh, this is the representation of general fixed point scaling. That is the scaling with respect to any other point, any other fixed point other than the origin. To d composite transformation, general 2D scaling direction. Scaling parameter were along x and y direction. What about the arbitrary directions? Let us see. scaling parameter S1 and S2 along orthogonal direction defined by angular displacement. You see here, this is S1 and S2, and uh, I have to now making a scaling reaction. So you coincide S1 and S2 with X and Y. You see the same thing is written. General procedure is rotate so that the direction coincide with the X and Y axis. So once it is coincide with the X axis, so we have to first making the rotation. So you see the object is there. So you see S1, S2. So we have to make the rotation so that S1 coincide with the X axis, S2 coincide with the Y axis. Rotate so that the direction coincide with the X and Y axis. Apply now the Keswick transformation. Apply scaling transformation. And once scaling transformation is done, because either in the X and the Y axis, two axes are there, so it is easy to apply the scaling factors. So once it is done, rotate back, inverse rotation. Okay. So these are the matrix, composite matrix. So matrix concatenation, some properties are there. You know that matrix multiplication is associative but not commutative. Matrix multiplication is not commutative, but it is associative. A composite matrix can be created by multiplicating left to right or right to left. But matrix multiplication not commutative as discussed. M2 into M1 not equal to M1 equal to M2. So that is why the homogeneous coordinate is used. Matrix concatenation property. Two successive rotation, two successive translation, two successive scaling are commutative. Let us see. You see, this is a tricky question. Two successive translation are commutative or not. For example, suppose there are two translation, translation 1, translation 2. If you first translation A or translation 1 followed by translation 2, as it give the same result if the order is changed. You first perform translation 2, then translation 1. You see here. Uh, this is the reversing the order. We have in which sequence of transformation is performed may affect the transform position of the object. In A, the object is first translated in X direction and then rotated anticlockwise through 45 degree. So you see the order. First translation, then rotated about 45 degree. You see the first is translated and then it is a 45 degree anti-clockwise, counterclockwise, anti-clockwise. So you will get then another. You see. But now I am changing the order. The object is first rotated 45 degree anti-clockwise and then translated. You see, it is first and then translated to X direction. So you see, you will get different position. So the successive translations is not commutative, may not be commutative. Commutative नहीं हो सकता. So you see, the final result or final position of two objects are different. So if we change the order, that is here is a first translated then rotated. In second row is first rotated then translated. You will get different result. So you can say here the successive transformation is not commutative. So far, we have discussed three different transformation: translation, scaling, rotation. Also, the translation, scaling, and rotation about the pivot point, any other fixed point other than the origin. And also learn that the successive coordinate transformation is not commutative. And also discuss that is the homogeneous coordination and why it is required. Now, besides that three transformation, another two transformation also there, important transformation. One is your reflection, another is your shearing. Let us see the reflection. Transformation that produce a mirror image of an object is known as reflection. You see here, this is x-axis and y-axis. This is there's a triangle. Its original position, you see that the represented by dotted line. If you will get another reflection image, that means if you put a mirror on x-axis, you will get that image. 1 dash, 2 dash, 3 dash is the reflection image or reflection position of the object 1, 2, 3. As we keep the mirror on the x-axis, this is called the rotation about x-axis. Rotation about x-axis. So this is the reflection about x-axis of the object. You see the object is in their original position 1, 2, 3, represented by the dotted line. After reflection, you will get on other position 1 dash, 2 dash, and 3 dash. So this is the reflection position of the original position. And as it is about x-axis, so it is known as the reflection about x-axis. Similarly, if we put on image in y-axis, this is called the reflection about y-axis. So reflection. Image is generated relative to an x-axis of reflection by rotating the object 180 degree about the reflection axis. So reflection axis is your x-axis. And you see the object is rotated around 180 degree, about 180 degree. So one is, you see, and in the previous one is in top position, but in reflection one is the bottom. You see the previous one. One is the top position, the original position, but in reflected position, one dash is the top. One another is in bottom. So reflection about line y is equal to 0, x-axis. This is the reflection matrix. 1, 0, 0, 0 minus y 0, 0, 0, 1. This is the simple. Similarly, this is the reflection about y-axis. You see now, if you keep a mirror in y-axis, you will get the reflected error, reflected image or reflected position of the object. So 1, 2, 3, which represent dotted line in the original position. If I keep a mirror on y-axis, I get the reflected position. So now the reflection is about y-axis or about x equal to 0 line. And this is the reflection matrix about y-axis. You see the minus y is there, minus 1, but in you compare with the previous one, minus is in the middle one position. Now minus 1 in the first row, first column. You see reflection about the origin. That is, if we keep the origin or the reflection about origin. So see here the original position and here the final position. 1, 2, 3, and 1, 2 is also there. So this is about origin, and this is the combination of x-axis and y-axis. Reflection about x-axis and y-axis. They both the sign have changed. So -1 is there, and minus is also there in the second row. Minus in the first row, and also in the second row. And this is the reflection about a line, any other line other than the x-axis and y-axis. So see, this is a line y is equal to x. Y equal to x means 0, 0. It passes to 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. Okay. So see, this is the line. In every point, the x-axis and the y-axis are equal. So this is known as the line y equal to x. In each point, the values of x coordinate and y coordinate are same. You see, it passes the origin 0, 0. Then 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, like that. So this is a line whose equation is y equal to x. And you see our original position of the object, which is dependent by dotted line. And the other, if we keep the mirror in that dotted the line y equal to x, we will get this image. And this is the reflection position about, and you see the matrix 0, 1, 0, 1, 0, 0, 0, 0, 1. So it forms the same quadrant. So that is why there is no minus sign in the matrix. So if you keep a image there, you will get the same image in the same quadrant. But to see, if we replace the above line y is equal to minus x, that is 0, 0, 1 minus 1, 2 minus 2, 3 minus 3, that position. So here you see there is a minus sign in the first row and second row. So if we keep that picture, you will see the object is there, and the sign had changed. So this is the reflection about line y is equal to minus x. Then 2D transformation, shear, last one is shearing. As you know, shearing is used to change the shape of the side. You see the image first. There is an image of a square whose point is 0, 0, 1, 0, 1, 1, and 0, 1. Each side is 1. Each size of sides are length 1. And whose coordinate you see 1, 0, 1, 1, 0, 1, and 1, 1. So this is a square. After using shearing, you see now the shape changes. Shape changes. It changes to a parallelogram, I think. Parallelogram. If we find area for both, it will be same. But you see the shape changes. The side of length changes, but the area must be same. The area of that and area of this is same. Okay, but you see now shape changes. Transformation that distort the shape of an object so that the transformed shape appears as the object was composed of internal layer that had been close to side over each other. So here I am using Sx factor 2. That is, I am sharing the factor x is equal to 2. So now we will get a new shape of the object. And x direction sharing related to the x axis is 1 SS 0 0 1 0 0 0 1. And the matrix is this, and the formula is x dash is equal to x plus shx into y. That means we're wrapping x direction that is related to x axis. Similarly, y direction is x dash equal to x, y dash equal to y plus x dash plus y. SHS dot x plus y. So x dash to sharing related to other reference lines. That is sharing with not respect to origins. Sorry, the x axis and y axis. So we using SSS into y reference. You see, this is a good example. Unit square is formed to be shifted parallelogram with SS is equal to 1 by 2 or 0.5. So if we are multiplying this and y reference equal to minus 1. You see, y reference equal to minus 1. So the first line should be, if we produce, it will pass through the minus 1. So unity square A is transformed to the shifted parallelogram. You see, after using the shearing formula, the side changes. The shape first was a unit matrix, there is a square, and now it is shifted to, now the side changes to, shape changes to a parallelogram using scaling factor 0.5. So you see there is no change in y axis. Y coordinate is same as original, only x changes. The y coordinate is not changes. If you compare the y coordinate of original position and the final position, the y coordinate does not changes. Only coordinate of x, because it is sharing is S. You are using SHX. That is the sharing factor about x axis. Similarly, x reference is equal to 1. Here the y remains same, but y changes. Okay. So please write your name and number, registration number in the board. Using mobile computing, mm, the features, the architectures of different technologies, that is your GSM, GPS, 4G, and 5G technologies, their advantages, their disadvantages, their data rates, and besides that, we have already discussed what is a internet protocol, what is mobile IP, and what is the work of mobile IP, what is the architecture of mobile IP, and how does mobile IP work. And also we have discussed some home smart equipments we are using in our home, and uh, how the sensor used in that equipment, and what is here the smart sensor. A smart sensor is nothing but it is a device that takes input from the physical environment and uses built-in compute resources to perform predefined functions upon detection of specific input on the process data before processing it. So it is nothing but it takes from input from the physical environment, it senses that and inform the user that this particular event already occurred, so that the necessary action will be taken. Uh, Smart sensor enable more accurate and automated collection of environmental data, which less erroneous noise amongst the accurately recorded information. These devices are used to monitoring the control mechanism in a wide variety of environment, including smart grids, battlefields, reconnaissance, explosion, and many science applications. The smart sensor is also crucial and integrated element in IoT. One implementation of smart sensor is as component of a wireless sensor and accurate network whose nodes can number of the thousands, each of the which is connected with one or more other sensor and sensor hubs. So it may be consist of other hubs which is known as the other sensor to perform specific tasks. And this is the block diagram of IoT sensor. It consists of different component. You see, so there is a IoT gateway access point or hub, and it is connected to the IoT sensor. You see, the IoT sensor of different it has sensor. The sensor may be a thermal sensor or sound or location or pressure sensor, whatever may be. This is sensor there, and it contain a microprocessor. That is, the microprocessor used, and beside that, some communication capability, either Bluetooth, RFID, or MQTT. So these are some communicative capabilities are used. Infrared. Cloud also includes some transducer, transceivers, or power source, and more. So these components have different function. Let us discuss that. A smart sensor has three components. A sensor that captures data. Once it is captured data, a microprocessor that compute the output of the sensor via programming or communication capability. Suppose, for example, a temperature sensor. It sensors the temperature, and the microprocessor it is compute whether this uh, temperature is okay or it is out of range, or it is more than the specified temperature. So that microprocessor that computes the on the output of the sensor, the output sensor is goes to the microprocessor, so microprocessor computes it. For this purposes, some programming and some communication capability also there. So a smart sensor might also include several other components besides the primary sensor. The component can include transducers, amplifier, excitation control, along filters and compensation. A smart sensor also incorporates software-defined elements that provide functions such as data conversion, digital processing, and communication to external devices. Besides that, the smart sensor also contain integrated communications capability that enable them to be connected to a private network or the internet. This enables communication to any external device which connected to the any uh, uh, private network or internet. What are different types of smart sensor? So know that the label sensor. A label sensor is used to measure the volume or space taken of a container. How much space already filled or taken by the liquid or any other things. So a vehicle's fuel gauge might be connected to a level sensor that monitors the level of fuel in the tank. If the levels comes below a particular height, so it already senses that and gives a information to the user that the levels of the fuels comes to below the particular level, so that the necessary action will be take place. Temperature sensor. A temperature sensor is a sensor that can monitor the component's temperature, so a corrective action can be taken if necessary. So in an industrial setting, for example, a temperature sensor can be used to make sure machine is not overheating. So when a machine is working, uh, so its temperature rises up. So if it is reaches gradually it increases, and if it reaches a certain fixed temperature, so the temperature sensor senses that and it stop the meeting automatically. So that is a uh, 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 so that it is sure that the machine is not overheated. Similarly, pressure sensor, which senses the pressure in a pipe or in a pressure sensor are often used to monitor the pressure of gases on a fluid in a pipeline. A sudden drop in a pressure might indicate a leak or a flow control issue. Suppose the pressure decreases, so it is assumed that there may be a leak or any flow control issue so that the pressure decreases. So the necessary action will be taken place. Infrared sensor. Some infrared sensors, such as those used in thermal imaging camera or non-contact infrared thermometer, are used to temperature monitoring. Non-thermal that is thermal imaging camera or non-contact infrared thermometer. So now the doctor are using this to measure the temperature of the patient. Other infrared sensors are optical sensor tuned in the frequency that enable them to see light in the infrared spectrum. This type of sensor are used in medical equipment such as pulse oximeter devices and electronic device designed to be operated by remote control. So this is also we are using in our home. Proximity sensor. A proximity sensor is used to detect the location of a person or object with related to the sensor. Basically, in a retail environment, proximity sensor can track the customer's movement throughout the store. So it track the customer move. Suppose there is a restricted area so that the customer cannot enter to it. Suppose there's a restricted area. So if the customer moves to that area, so the proximity sensor senses that. So so that the necessary action will be taken. Basically, we know sensor and actuators. Second, sir, actuator in associated with the robotic engineering. So sensor and actuator allow robot to achieve certain tasks. Example of that, what the robot may need to determine include how far it is going, in what speed the robot is moving, if the robot is in the hill, at what angle is it, if the robot is rotating, by how much has it rotated, where is the robot, or in what direction is it going, how far it is traveled, how much power it is consuming. It is for internal sensor, how power, and all are the external. What information is being communicated to the robot. So as we discussed, some external sensor is used to measure the other object. For instance, how far away is an object and where the object is. And internal, as the name suggests, internal sensor, it is used to measure the robot itself. Okay, how much power it is consuming, the angle of the robot, how fast it is going. So there are two type of sensor used in a robot. One is external, which senses the external component, and what the internal sensor, which senses the internal component of the robot. Actuators. An actuator is a device which causes something to happen. This could be robot movement, which is often achieved using motors. An actuator is needed to make the robot wheels turn, or the joint of the robot arm to rotate, or for a robot gripper to open or close. These are the function of actuators. Or it could be the let the others know what the robot is doing. A light being turned on to indicate the robot is working. Sound is being emitted, so the actuator is a loudspeaker. It's also a loudspeaker sometimes, so some sound will be emitted. Communication is formed, so a transmitter is required. Sometimes there need a communication, and also it needs some display. So an LCD screen for showing the picture and other of data. So all include in the actuators. Smart home appliance. We know that we are using some appliance nowadays in our home, uh, and it is smart in nature. Smart in nature sense there are some sensor used for it. It automatically works. There no need of any human interface. Interfere. There no human interfere. A smart lawn mower. You may seen in the TV or you may seen physically. A high quality lawn mower needs rigorous motor control and sensing, high efficiency, secure connectivity, and high reliability and robustness. You are using your mobile phone or any remote controller uh, to operate in this lawn mower. Using a safe wireless connection to the smartphone, lawn mower are used to easily prolonged to make its best use of their lifespan and presentation. So using your smartphone or using any other communication device, you can operate a lawn mower. Smart refrigerator. A normal quality type refrigerator used to high reliability and robustness, high efficiency, safe and accurate sensing. The entails the expansion of refrigerator with the last default cycle. If it is automatically defaults or automatically stops, stable wireless connectivity and higher user occurrence work on smart home automated technology. So nowadays, all the other appliances also use in a smart TV. You are using smart fan also available nowadays. So which automatically was by your any other communication device by a smartphone. You are operating a TV by using a smartphone. You are operating your AC using smartphones. PLMN, Public Land Mobile Network. The PLMN is the term used to describe all mobile wireless network that use earth-based station rather than satellites. So that is why it is public land mobile network. That is, there no satellite is used. They are using the land-based station. PLMN is the mobile equivalent of the PSTN, such as a system can stand alone, but often it is interconnect with a fixed system, such as the public switches telephone network (PSTN), public switched telephone network. The most familiar example of PLMN's end user is a person with a cell phone, not a mobile phone with a cell phone. However, mobile and portable internet use as common. Uh, a public land mobile network is identified by a globally unique PLMN code which consists of a MCC mobile country code and MNC mobile network code. Hence, it is a 5 to 6 digit number identifying a country, and a mobile network operator in the country usually represent the form 00101 or 001 or 001. A PLMN is a part of a location area identity, public land mobile network, and location area code. Cell global identity CGI, IMSI, and PLMN are the other codes. So using, you see, some of technology we have already uses. A public land mobile network typically offer the following service to mobile subscriber: emergency call to local fire, ambulance, police station, medical, like that. We have the some emergency call it automatically there, and you can easily connect them to call the local fire station or local ambulance, local police station. Voice call to from any PLM or cellular network or PSTN or VoIP. So you can make any voice call. Besides that, you can send any message, SMS services also, to and from any other PLMN or SIP services. So you can send data SMS in the form of text data or any multimedia data. Multimedia messaging service. Any multimedia, you can send any audio or video receive to or any MMS multimedia service to from any other PLMN or SIB service. Besides that, some USSD code is also there. You know that I am using some USSD code to get some service. We basically use this code to find our to get our balance, to get our how much data we have already used, on how many data or how much time, call time is there in our uh, set. That is called unstructured supplementary service data, USSD. So basically it is used in hash 123, hash 12 something. So for operator specific interaction, dialing star hash 100 hash to indicate the current balance. So it is different from to operator, but this USDSD code is also another service of PLMN. Internet data connectivity for arbitrary services via GPRS or in GSM, LUPS and UMTS, and also LT. We already discussed this the technology LT, GPRS, GSM in our previous slide. High speed circuit switcher data, HSCSD. High speed circuit switches. So it is using circuit switches, but the speed is enhanced. Speed is increases. It is an enhancement of data rate of circuit switcher data in a GSM network. HSCSD uses two techniques to increase the data rate. As the name suggests, the data rate is increased as compared to a GSM network. So let us how it uses two techniques to increase the data rate. The first one, it makes possible to use more than one time slot. GSM use time division multiple access, TDMA. So you know that there are different type of technology are used for multiplexing. TDMA is one of them. FDMA, TDMA, we can also use, we discussed in the last classes. So each radio channel is divided into 8 time slots. Each time slot is allocated to a different user. So that is why as more time slots are divided into different slots, so each time slot is given to different user. This makes it possible to serve 8 customer on one radio channel. So yeah, it is divided into different slot. So it is possible to serve 8 customers in one radio channel. HSCSD make it possible to allocate more than one time slot to a user. It is also possible to allocate more than one time slot to a user. The second technique is used by it is that the error correction can be adapted to the quality of the radio channel. So error correction also is adapted. Some technique is used to detect and correct the error. A standard slot can carry 9.6 kbps. HSCSD makes it possible to increase this to 14.4 kbps. The quality of the radio channel must be good enough to do so. The maximum data rate here is with the HSCSD configuration with 14.4 kbps channel, coding is 115 kbps if all 8 time slots are allocated to the same user. So if the same user or if the other user are there, so it may be decreased. The main benefit of HSCAD compared to other data enhancement introduced later is that is an inexpensive way to implement higher data rates in GSM network. So in GSM network, which an initial data was very slow, but it an inexpensive way. The cost is also here not more, it is minimized. their modification to be made are relatively small. Then the next and important topic is WLL, wireless local loop. Let us see what is local loop. Local loop is a circuit line from the subscriber phone to the local central office. So, but the implementation of local loop of wire is risky for the operator. So initially, there's a wire particular line, a circuit line from the subscriber phone to the local central office. But the implementation of the local loop of wire, if there is wire or physical cable, it is risky for the operators, especially in a rural and remote area due to less number of users and increasing cost of installation. So if the physical installation there, the cost will be more. So it is risky for the operator. Hence, the solution for the users of wireless local loop. So we are using this as wireless, which uses wireless link rather than copper wire to connect subscriber to the local central office. So this is wireless. So it uses wireless loop or WLL, wireless local loop rather than the physical copper wire to connect the subscribers to the local central office. Initially, there's some copper wire is used, physical cable was used, which was more cost, which is not cost effective. So in place of that, WLL used for this purpose. You see here. So there is the architecture of WLL. Local exchange office transceiver, which is connected to the WLL, and this is the home subscriber home. You see, and this is wirelessly connected. There's a link, wireless link to the home to the local exchange office, and once it is connected, so now you can communicate with the other network and with internet. Let us discuss the component of in this architecture. You see there are some PSTN. In previous slide you see PSTN is there. It is public switcher telephone network, which is a circuit switcher network. It is a collection of walls interconnected circuit switcher telephone network. It is a connection of walls interconnected circuit switches. Switch function. Switch function switches the PSTN among various one nodes. What is JANU? Now, Wireless Access Network Unit. It is short from Wireless Access Network Unit. It is present at the local exchange office. All local WASU, that is Wireless Access Subscriber Unit, are connected to one WNU. Its function includes authentication, operation, and maintenance, routing, transmitting voice and data. So once you connect your WASU with WANU with the local office, so all this function, that is your authentication, whether you are a authorized user or not, operation, maintenance, all are connected through or not, or routing, if a packet comes or data comes, it is routing or transmitting voice and data. So transmitting the voice and data also, these are responsible. WNU is responsible for that. You see the image in previous WNU, which is contains some other component transceiver there, where WL controller there, and it is local exchange office. WASU. It is short from Wireless Access Subscriber Unit. So it is available along with the subscriber unit. It is present at the house of the subscriber. It connects the subscriber to WANU, and the power supply for it is provided locally. So you see the picture WASU. It is WASU is available in the home, subscriber home, and it is the power supply to is locally at subscriber home, and all the services, voice services, fax, modem, data are connected to WSU. And any data from the home is go to WSU, and it is connected to WANU local exchange office. Advantages. It eliminates the first mile and last mile construction of the network connection. So it eliminates that the range. That is low cost due to no use of conventional copper wire. The cost is cost effective because no conventional copper wire is used by the subscriber, sorry, by the uh, subscriber, by the, so the risk is less and the cost effective also. Much more secure due to digital encryption technique and using wireless communication. So it is more secure because it is digital encryption is there. High scalable as does not require the installation of more wire and scaling. So it is scalable. That is, there's no, as there's no physical wire, it is scalable. If it is physical wire there, so there need, if the it is not scalable because if you need extra range, so you have to add some physical wire. So as it is as WL is wireless, so it is scalable in nature. And the feature of WLL is internet connection via modem, data services, voice services, and fax services. So these are also feature of WLL. There are two types of WLL. LMDS provide services, high-speed internet access, real-time multimedia file transfer, remote access to the local area network, interactive video, video on demand, video conference, telephone services. MMDS can transmit video, voice, data signal at the rate of 1.5 to 2 Mbps downstream and 320 kbps. So depending upon the speed, the application of WLL in total is LMDS and MMDS. Then 4G and 5G networks. High speed packet access, HSPA, refer to set of technology that come about as a result of enhancement to wideband code division multiple access system. So we already know the CDMA technology. So it is wideband code division multiple, that is WCDMA. HSPA is composed of high speed download package access HSTPA protocol and high speed uplink packet access protocol. It features peak data rates up to 14 Mbps downlink and up to 5.7 Mbps uplink. And another technology is MIMO, multiple input, multiple output. Let us see how does it work. MIMO is an antenna technology for wireless communication in which multiple antennas are used at both the source transmitter and the destination receiver. So multiple antennas used in both sides, source as well as the receiver. MIMO communication sends the data, send the same data as several signals simultaneously through multiple antennas, while still utilizing a single channel. We have an image, we'll discuss about that, but it is the same data as several signals simultaneously through multiple antennas. As there are names such as multiple inputs, this is form of antenna diversity, which uses multiple antennas to improve signal quality and strength of an RF link. Let us see. You see the architecture, the LT is NB with 4 transmitters and receiver also with 4 antennas. And this is the radio transmission path. And you see there's the high data rates and improved throughputs. They are using multiple input and multiple output. So it is capable of four. It is known as 4x4 MIMO. The data is split into multiple data streams, and the transmission point and recombine and the receive side by another MIMO radio trans configuration with the same number of antennas. Okay, so you see, so the data is split into multiple data streams at the transmission point, and obviously it is recombined on the other side or receive side by another MIMO radio configured with the same number of antenna. So the receiver is designed to take into account the slight time difference between the recipient of each signal, any additional noise or interface, and even lost signals. So the benefit we'll get here is it is improved throughputs and obviously high data rates. So you see data transmitted and split into different and also it is recombined in the receive sites using radio confused antennas. The some other technologies, WiMAX and LT, long-term evolution, we know. Let us discuss what is WiMAX. Worldwide interpretability for microwave access is a telecommunication technology aimed at providing wireless data over long distance in a variety of ways, from point-to-point links to full mobile cellular type access. WiMAX and LTE are both wireless network technology. So you know that is LTE and both are the wireless network technology suitable for data connection to mobile and some other devices. WiMAX is an IEEE standard 8021.6. Its original name is Wireless MAN for Metropolitan Area Network, and this name appears intermittently in IEEE standards. So these are some technology used for data communication. LT, we know that there are 4G LT uh, was first introduced in 2008. It defined a new cellular access. So you know that after 3G, 4G and 4G LTE was used. Please recall, we have discussed that 4G LTE. So it is a special efficiency, high speed data rates, short round trip time, as well as flexible in frequency and bandwidth. It signifies an evolving level of performance as the capability of cellular hardware, software, network technology, such as speed, latency, battery uses, and cost efficiency. So it is speed as more speed as compared to the other technology used at a time. Latency means the time interval between the data sent and data received. So it has the better enhanced latency. Battery usage is also better, and also it is cost efficiency. So these are the features of LT. Besides that, LT technology has delivered multiple benefits worldwide. LT connectivity is almost universally available around the world for both consumer and commercial and industrial application. LT provides long-term network continuity as older networks such as 2D and 3D sunset. So you know that after 2G or 3G, so LT is available around the 4G or after 4G. So in regions where 5G not be available for some time, 4G LT or 4G LT Advance and 4G LT Advance Pro technology will be support migration next to 2G 3G for the year to come. So after 2G and 3G, where 4G technology we are using, so at that time the LT along with the 4G LT, LT Advance or LT Advance Pro technology are used to enhance the data rates. Besides that, LT offers higher speeds as well as significant benefit for low power application and simpler low cost devices, providing a single technology foundation for a wide variety of use cases. So it is beneficial for a low applications and simpler low cost devices. So here are a few important facts to know about how LT works at a high level. LT offers lower latency. The latency is lower. Latency means that is we have already discussed the data between the time between the data sent and data received, and it has lower latency means data speed, there's the speed of data, so that latency is less, and increased throughputs throughout the network, dramatically improving upon 3G network perpendicularly. So data rates are increasing over 2G and 3G network. The speed is better as compared to G compared to the 2G and 3G network. LT operator on a separate spectrum from 3G network and requires new hardware. So it operates on a separate spectrum from the 3G network. So that is why it requires a new hardware. LT provides fast data download speed of several hundred megabytes per second compared to several tens Mbps in 3G. So basically, it is the data speed rate is 10 more than 10 times as compared to 3G, meaning that LT is 5 to 10 times faster than 3G. So the LT is about 10 times faster than the 3G. So LT can support data voice, VoLT, instant messaging, and video on smartphone and tablets over a single interface. With 3G, these were done over different systems and some on some network, voice and data was mutually exclusive. Means at the same time, the mutual exclusive means voice and data cannot be sent or cannot be communicated at a time. So so this is mutually exclusive data and mutual exclusive. So LT can support the data voice rates, instant messaging, voice video on a smartphone and tablets over a single interface. But as compared to the 3G, this were done over different systems and on some network, voice and data were mutually exclusive. That is, they simultaneously they can occur. So the difference between 3G and LT, so first factor comes as it is speed. Obviously, 3D is slower with data rates measured in kilobytes per second, where it is megabytes per second. So obviously, the speed is of a LT technology is better than a 3G technology. Latency, the 3G latency, the gap between when data is sent and when data is received. So latency means the latency word means the time gap between the data is sent and when the data is received is much greater. Power uses. LT device transfer a higher volume of data and can therefore use batteries faster than 3G, which has cost and power management. Implication that developer and network managers must take into consideration. So it uses more power as the data transfers higher volume, so it consumes more power. So therefore the battery is faster than 3G. Availability, use and reliability. 3G network until recently were more widely available. Today, 4G networks are nearly universally available and the reliability difference have largely disappeared. So nowadays, 5G also, okay, the another term is ultra wideband. What is ultra wideband? UWB. It is a short range of wireless communication protocol that like Bluetooth or Wi-Fi. So you know that Bluetooth communication is a short range. It has some range. You can communicate through Bluetooth if you are within that range. Beyond that range, it cannot be accessed. Or Wi-Fi also. Wi-Fi has also some range. So if you goes outside of that range, you cannot access the Bluetooth or Wi-Fi. So WB is a short range wireless communication protocol used for short range, like your Bluetooth or Wi-Fi. Uses radio waves, but it differs substantially in that it operator at a very high frequency. As its name denotes, it also uses a wide spectrum of several gigahertz. So basically, it is a communication protocol used in short range distance, like your Bluetooth or Wi-Fi, with which are used nowadays, widely used nowadays. The fifth generation. So we have already discussed 1G, 2G, 3G, and 4G. 4G LT, LT Advance, Advance Pro, and sometimes it is got 2.5, 3.5 GB, 5G technologies. The 5G enables a new kind of network that is designed to connect virtually everyone and everything together, including machine, object, and devices. 5G wireless technology is meant to deliver higher multiple Gbps peak data speed, more reliability, massive network capacity, increased availability, and a more uniform user experience to more users. Higher performance and improve efficiency, empower new user experience, and connects new industry. And you know that these are the massive features of 5G. Enhanced mobile broadband, more informed data rates, obviously lower latency, that is mean that time gap, and lower cost per bit. It is also cost effective. Mission critical communication, 5G can be enable new services that can transform industry with ultra reliable, available low latency links like remote controller or critical infrastructure, vehicles and medical procedures. So you know that nowadays 5G network or 5G technology use and massive IoT. 5G is meant to seamlessly connected a massive number of embedded sensor in virtually everything through the ability to scale down the data rates, power and mobility, providing extremely lean and low cost connectivity solutions. अच्छा, then mobile IP. We already discussed the mobile IP. How does mobile IP that this work? But now we see how it works. We have already discussed what is mobile IP. Mobile IP is an internet protocol basically used for mobile devices to communicate with others without dropping or disturbance in the communication. We are not dropping the communication if we are moving while we are leaving one network and entering another. So there is no loss of communication. There is no drop of communication. We can continue our communication because of this protocol, mobile internet protocol. We have discussed it that how it is mobile IP, it is internet protocols. So let us see how it is works. We have also learned that different terms are used. That please recall, home agent is there, your foreign agent is there, correspondent node is there. You see, the correspondent node send the data to the mobile node. So there are two terms we have already discussed. A correspondent node send the data to the mobile node. Mobile node suppose your phone and the correspondent node suppose your friend's node or friend's mobile. Suppose your friend is now want to send data to you. So your friend mobiles is considered as the correspondent node and your mobile is considered as a mobile node. Data packet contain the correspondent node's address. So the data packet which comes from the correspondent node, what does it contain? Correspondent node's address, the source address, and the home address, the destination address. Packet reach the home agent first. So the packet which contains these two things along with data, it contains the source address and the destination address. So suppose when we are sending a letter via post office, you have to write the destination address and also you have to write the sender address. So that packet contains the data as well. Besides the data, it contains the address, sender address, and receiver address. But now the mobile node is not the home network. This is the problem. Suppose you are staying in your home, your post office or postman belongs to a local post office, knows you, he immediately deliver data to you in your home. But the problem is you are not in your home. You have already moved to other location. So, but now the mobile node is not in the home network. It has moved into the foreign network. The foreign agent send the care of address to the home agent to which all the packets should be sent. So the foreign agent send the care of address. So this is the temporary address of your node which comes under me, and please send the packet to this address, this new address, and this address is known as care of address to the home agent to which all the packets should be sent. Now a tunnel will be established. A dedicated path, a tunnel will be established between the home agent and the foreign agent by the process of tunneling. As we discussed the last class, a tunnel is a dedicated tunnel is established between the home agent and the foreign agent, and this process is known as tunneling. Key mechanism. Then please. Uh, First, the agent discovery. Agents advertise their presence by periodically broadcasting their agent advertisement message. The mobile node receiving that agent advertisement message observe that the message is from one home agent and determine whether it is an home agent or foreign agent. So this agent advertise their presence. So the mobile node uh, receiving the agent advertisement message observes whether the message is from the home agent or foreign agent. Agent registration. Mobile node, after discovering the foreign agent, sends a registration request. That is, I am now entering your area, now register me. RRE2 to the foreign agent. So once the request comes, the foreign agent in turn send the registration request to the home agent, which is the care of address. So the foreign agent send the registration request to the home agent. That is the mobile node, which is originally belongs to you. Now in my network, and this is the request he has sent, the mobile node has sent for registration. So it sends that to the home agent and with the care of address, and this is his new address. The home agent sends a registration reply to the foreign agent. It is okay. I know that my mobile node, which belongs to initially first, it is in your network. So then it forwards the registration reply to the mobile node and completes the process of registration. Tunneling. It establishes a virtual pipe for packets available between a tunnel entry and tunnel endpoint. So there is no other interfere between the tunnel. So the packets are sent through the tunnel from one end, and it is delivered in the other end. So it is the process of sending a packet via a tunnel, and it is achieved by a mechanism called encapsulation. So know that encapsulation is a property. It takes place of forward and IP datagram from the home agent to the care of address. What is care of address? The care of address is the new address of the mobile node. So once a packet comes, so during the process of registration, the home agent knows that this is the new address of the mobile address. So any data come from the correspondent node now, it is sent that tunneling with that new care of address. Whenever the home agent receives the packet from the correspondent node, it encapsulates the packet with source address as home address. The source address is the home address and destination are the care of address, the new address. Okay, so the new address. The destination is the new address, care of address, which are generated during the process of registration. You see, there is a home network. Home network in the left side, there is a home agent also. Similarly, then foreign network and foreign agent. So now you see the mobile node is present in the foreign agent. Initially it is on home agent. So if it was in home agent, there is no problem. Any data come from the correspondent node reaches the home agent. So if it was in home network, there is no problem. Home agent directly deliver data to the mobile node. But the problem is the mobile node now belongs to the foreign agent. And there is a registration between the foreign agent and home agent. Home agent send a new address of mobile node, that is called the care of address. So now suppose the correspondent node send data to the mobile node. So data first come to the home agent. Home agent note that mobile node now is not staying or not belongs to my home network. It was in the foreign agent. So immediately you see a tunnel will be established. And the packet along with the home address is encapsulated and put one end of the tunnel and is delivered to another node of the delivered to the another endpoint to the home agent. So now the packet recharge foreign agent from the home agent. Foreign agent know the address of mobile node. So it deliver data to the mobile agent, mobile node. So mobile node gets it. And there is an acknowledgement from the foreign agent to the correspondent node directly. You see, the foreign agent, there is a acknowledgement from the foreign agent to the correspondent node. You see, there is arrow mark from foreign agent to the correspondent node. So this acknowledgement goes to the correspondent node from the foreign agent, not from the mobile node or home agent. But the correspondent node deliver data to the home agent, but gets the acknowledgement from the foreign agent. So getting acknowledgement, home agent does not play any role. Does not play any role. It receives data from the correspondent node, forward to that packet to the foreign agent through the process of tunneling, and the foreign agent is responsible for forwarding data to the mobile node. Once it is received the mobile node, the foreign agent send the acknowledgement to the correspondent node. And in this way, the communication takes place, although the mobile node is not present in the foreign agent. Let us discuss the process of tunneling. Tunneling establishes a virtual pipe for the packets available between the tunnel entry and tunnel endpoint. As I told, there is no interface between the any other points of the tunnel, so that is why I call it the virtual pipe. Only at one end the packet will be delivered, in the other end the packet will be received. If the process of sending a packet via a tunnel and is achieved by the mechanism called encapsulation. So the care of address along with the data, along with the home address. So it is behaves as a single unit, tied in a single unit. It is known as, the process is known as encapsulation. The home agent encapsulates the data packet into a new packet in which the source address is the home address and destination is the care of address. The source is the not the correspondent node. The home is the home address. Home address is the source address because home agent sending data. No doubt the data originally comes from the correspondent node, but the source address is the home address. And what is the destination address? Destination address is the care of address. The new address was generated during the registration of the mobile node. So the three things is tied, is encapsulated. What is that? The data packet itself, the source address as home address or destination address as the care of address. Care of address, home address, and the data packet itself. What is home address? Home address treated as the source address and care of address is treated as the destination address. So and send it through the tunnel to the foreign agent. So foreign agent receives three things, the three component of the data: data itself, the address of the home, and address of the destination, that is care of address. So foreign agent on another side of the tunnel receive the data packet, but the data packet contains three component. So it have to decapsulate it. It open the tie. It is tied that by the home agent. So when receiving the foreign agent, so it decapsulated them and send them to the mobile node, data to mobile node, because the destination address is no. So it send data to the mobile node. The mobile node, in response to the data packet, receives, sends a reply to respond to the foreign agent. So after getting the data, you see, after getting the data, there is an arrow line from foreign agent to mobile node. So foreign agent deliver data to mobile node. Once the mobile node receives the data, it sends a acknowledgement to the foreign agent, and foreign agent send that acknowledgement to the correspondent node. So foreign agent on another side of the tunnel receive the data packet, decapsulate them, and send them to the mobile node. The mobile node, in response to the data packet received, sends a reply in response to the foreign agent, and the foreign agent directly sends the reply to the correspondent node. Okay. So in this way, the mobile IP works. Route optimization in mobile IP. The route optimization adds a conceptual data structure that binding cache to the correspondent node. The binding cache contains binding for the mobile node's home address and its current care of address. So that binding cache contains nothing but it is for mobile node's home address. So as we discussed in the previous slides, it contains that packet contains the data itself, the home address, that is the as source address, and the care of address as the destination address. Every time the home agent receives an IP datagram that is destined to a mobile node currently away from the home network, it sends binding update to the correspondent node to update the information in the correspondent node's binding cache. So every time it's currently away from the home network, it sends a binding update to the correspondent node to update the information to the correspondent node's binding cache. After this, the correspondent node can directly tunnel packet to the mobile node mobile IP is provided by the network provider. So that means if now the correspond data send data, it doesn't come over the to the home agent. So this correspondent node can directly tunnel packet to the mobile node. So this is the route optimization. That is previously what was done. That is the correspondent data send data to the home agent. Home agent make a tunneling to the foreign agent. Then data comes to the foreign agent. Then it delivered to the. But if the every time the home agent receives an IP datagram that is destined to a mobile node currently away from the home network, it sends a binding update to the corresponding node that is I am changing my location. So my address is already changed. So to update the information in the corresponding node, suppose you are now staying your permanent address. You have suppose moved to one location. Suppose you are staying in Delhi. Now you move to Mumbai. So you immediate update that data to their friend that I am in Mumbai, so that he can directly send data to you. So after this, the corresponding node can directly tunnel packets to the mobile node, and mobile IP is provided by the network provider. So this is the mobile IP. So we have already mobile IP, we have learned mobile IP, mobile IP structure in the previous classes. So now the working principle with a suitable picture as a diagram. Okay. So this is the working principle of mobile IP. Then the next is cellular IP. Let us see what is cellular IP. The, uh, the mobile IP protocol we have just discussed is considered to have some limitation in its capability to handle large number of mobile stations moving fast between different radio cells. If the mobile nodes frequently change or fastly change its location, and a large number of mobile stations moving fast between the different radio cells, so here the performance of mobile IP degraded. The handover frequency should typically not exceed once a second. However, mobile IP is well suited for interconnecting disparate cellular network effectively, providing global mobility. Resulting from this, some micromobility approach have been proposed within the IETF, which support mobility in a well-defined area. Four fundamental design principles of the protocol are: location information is stored in distributed databases. So all the location information is stored in a database, distributed database, so that we can use it. Number two, location information referring to a mobile host is created and updated by regular IP datagram originated by the said mobile host. So location information is stored as soft state. Location management for idle mobile host is separated from location management of hosts that are actively transmitting or receiving data. So if the large number of nodes are changing data frequently or very fastly, uh, in place of mobile IP, cellular IP performance is better. You see, you see the corresponding host is there who is sending data to the mobile node. Mobile node may belongs to home network or foreign network. So if it is in home network, there is no problem. It is data comes from the corresponding node to the home agent. You see, they are connected to the internet. They are globally connected. So if in your foreign network, if the data comes from the corresponding host, the home agent routers is responsible for sending data to gateway router of cellular IP. So once the cellular IP gateway routers or foreign agents receive that data, so it is delivered to the mobile node which belongs to this network. So another new protocol, IPv6 mobility. Many times this question comes. Write a short note on IP version 6, IPv6 mobility. Let us see what is IPv6. When a host is connected to a link or network, it acquires an IP address. You know that. Suppose there is a network. If you connected any node to a network, it acquires an address that is known as IP address. Once it gains that IP address, once it gets that IP address, so the rest of communication take place via through this IP address. So when any node, a host is connected to a link or network, obviously it acquires an IP address. Suppose if you connect your mobile, your laptop in a network or internet, it acquires an IP address. And once it receive or gets in IP address, all communication take place using that IP address on that link. As soon as the same host changes its physical location, that is moves into another area, subnet, network, the IP address changes accordingly. And all the communication taking place on the host using old IP address goes down. So the old IP goes down. So IPv6 mobility provides a mechanism for the host to roam around different links without losing any communication connection and its IP address. So if that node is moving to other network, it acquires a new IP address and the all the communication taking place on the old IP address which goes down. So that is why to overcome this demerit, to overcome this constraint, IPv6 mobility provides a mechanism for the host to roam around different links from one link to another, from one network to another, without losing any communication connection of this IP address. So this is the best feature of IPv6. The same mobility operation, when mobile node stays in the home link, all the communication takes place on its home address, there is no problem. So see here, the home link is there, the correspondent node send data to the home link. So home agent is there, it immediately deliver data to the mobile node. So as long as the mobile node present in the home link or home address, there is no problem. There is no need of a foreign link or foreign agent. But as soon as when a mobile node visit the foreign link, visit the foreign address, so at that time the mobile IP or mobile IPv6 or cellular IP does it works. So when the problem arises, when a mobile node leaves its home link and is connected to the some foreign link, the mobility feature of IPVs come into the play. So when it leaves the home agent, home network and enter a new network, a foreign network, so the mobility features of the IPVs come into play. So it is called the IPVs mobility. After getting connected to the foreign link, the mobile node acquires an IPv6 address from the foreign link. This is called the care of address we have already known. The mobile node send a binding request to its home agent with the new care of address. The home agent bind the mobile node's home address with the care of address, establishing a tunnel between both. So it form an home agent, the same discussed in the previous slides. Agent with a new care of address. So this is the home agent known there. This is the new care of address, new address of the mobile node. So now the mobile node does not belongs to the home network. It belongs to a foreign network, and it is here the new address. That address is referred as here care of address. The home agent bind the mobile node's home address with the care of address, establishing a tunnel between both. Whenever a correspondent node tries to establish connection with the mobile node on its home address, the home agent intercept the packet and forward the mobile node's care of address over the tunnel which has already established. So in second step, you see the tunnel has established. So any correspondent node try to establish the connection with the mobility node. The home agent interpret the packet and forward to the mobile node's care of address over the tunnel which was already established. You see here. You see the mobile nodes now belongs to the foreign link. So there is a correspondent node now sending data to the home agent. But as the mobile node does not belong to home network, so there is a tunnel established between the home agent and the mobile node. There is no, you see, there is no foreign agent. So direct tunnel established between the home agent and the mobile node. So once the correspondent node sends the data, uh, the data is forwarded to the pair of address through the tunnel, which has already established in, which has already established. So this is the working principle of IPv6. This is the IPv6 mobility, and you may get a short notes on IPv6 mobility. I saw the previous papers where the IPv6 uh, some is several times asked what is IPv6 mobile mobility and what is the features. So these protocols, that is your cellular IP or mobile IP and IPv6 is used to for a mobile device to communicate. So please write your name and registration number in the board. Please wait a while. I'll take a snapshot. So I think your MCS 230 classes are over. So next three classes in next week, one in on Saturday, another two in Sunday. I think it is for MCS 231. So in the next class, we will discuss the different technologies and other VoIP and other technologies are there. So any problem or issues you can ask.
Sir, can you share us this PPT?
How? How can I share? Can you give your email ID or how can you share?
Yeah, I will paste my ID in chat.
Yes, you write your mail ID.
Hmm.
I will send the PPT for both 230 and 231.
Okay.
So you can share if you are if you have any groups or you can share them so that the other student can use.
Sure, sir. I will share in group. Hmm.
Okay, so you write
Thank
your
you.
email ID in the board. I will take that and I will send today.
Yeah. Okay. I have shared.
Okay, okay. I got that. So I will share that.
Oh,
Uh,
thank
so okay, thank you to all. Thanks, and meet in the next class. Let us leave. Okay, you may write the other students may write your email ID so that I can share at a time.